Hey y'all, today's lesson is going to be about linear functions and identifying some of the characteristics of those linear functions. So before this lesson, we focused on functions in general and we learned how to identify whether something was or was not a function. We learned how to recognize domain and range of a function, whether it was increasing or decreasing, constant, that kind of stuff. Now we're going to focus specifically for a while on linear functions. So linear functions, remember, are those functions that graph always as a straight line. That's what makes them linear. That word linear means line. And so they have some specific characteristics, and we want to make sure that we're able to identify what those are. So by the end of this lesson, you should be able to classify functions as linear or nonlinear. And you should also be able to identify the slope of a linear function and the y-intercept of it. Now, you will have done most of this in your 8th grade math class last year. Because when I taught 8th grade math, we did a lot with linear functions. That's really the only kind of functions you focus on in 8th grade math. So hopefully some of this is somewhat familiar to you. But it may be that you don't remember as much as you need to, and so we will kind of work to refresh some of that and hopefully learn some new things today. So, a linear function is any function that graphs as a straight line. It has to be a single straight line, not like two straight lines together, but a single straight line is a linear function. They always have a constant rate of change. Constant means it stays the same. A rate of change is how it's increasing or decreasing over time. The most common word that we use for rate of change in Algebra 1 is slope. And all linear functions can be written as an equation in the form y equals mx plus b. Now, they're not always in that form, but they all can be written in that form. That's called slope-intercept form. A lot of times we'll see them in a different form. Sometimes you're going to also see them in what's called standard form, and that looks like ax plus by equals c. So that's where your x and your y are on the same side, and you have a constant term on the end. Both of those would be considered linear. So whether it's in slope-intercept form or standard form, this is slope-intercept. This is standard. Both will represent linear functions, and we'll look a little bit more closely at that in just a second. So straight lines with a constant rate of change and possibility of being written in y equals mx plus b form all make something linear. So to test to see whether something is or is not linear, we've got to kind of look at how that function is represented. So functions can be represented as graphs or tables or equations. Could be all three of those things. So we need to look specifically at whichever one we're looking at in particular to decide whether it's linear or not based on the characteristics of that particular thing. So if we're looking at a graph and trying to decide whether it's linear or not, it's really, really simple. If it's a straight line, it's linear. Now, nonlinear does not have to be curved. It could be like V-shaped or zigzag-shaped, U-shaped. Any of that would be considered nonlinear. So as long as it's not straight, it's nonlinear. You might say, was it not straight curved? Not necessarily. A curve is like a curve, you know. But it could also be like V-shaped and still be considered linear, because that's also another way to be not straight. So that's what we look for with linear or not in a graph. You just look at the graph, decide if it's linear or if it's nonlinear. So if you look at this one right here, the one on the left side is linear because we see that it's a straight line all the way through. Now it's diagonal. That's fine as long as it's straight. And then this other one is nonlinear because it has this curve in the middle that makes it nonlinear there. So graphs are probably the easiest ones to be able to tell. I don't know how I zoomed in. I can't zoom back out. Wait. Oh, just kidding. Reset. Okay. Sorry, y'all. Graphs are probably the easiest one to be able to tell. Tables maybe are one of the tougher ones to be able to tell because in a table you have to look at the rate of change in it to make sure the rate of change is constant. So you have to do a little bit of calculating from a table to be able to know. So if it has a constant rate of change, it's linear. If it has a variable rate of change, that means it's not constant, it's changing, then it's nonlinear. Sorry, I had to pause you for a second. So let's look at what that means when we talk about rate of change. In a table, if you're trying to figure out the rate of change to determine if it's constant or variable, you want to look and see how much things are changing across the x values in the table and how much they're changing across the y values in the table. So the easiest way to do this is to just look from point to point to point to see how it's increasing or how it's decreasing. So if you look in these x's, to go from 0 to 1 increases by 1. To go from 1 to 2 increases by 1. To go from 2 to 3 increases by 1. And then we look for the same thing in the y. To go from 0 to 1, we increase by 1. From 1 to 4, we increase by 3. From 4 to 9, we increase by 5. So to determine the rate of change from that, you would divide the change in the y by the change in the x's. And if you get the same number every time you divide that, you have what's called a constant rate of change. If you get a variable number or a different number every time you divide that, you have what's called a variable rate of change. So the change in the y's gets divided by the change in the x's. That little triangle is a delta symbol. That's mathematical. But the delta symbol means the change between. So if I was going to do this with this, I would do 1 divided by 1 and get 1. And then I would test my next point. 3 divided by 1 would give me 3. 5 divided by 1 would give me 5. So between these 3 different sets of points, I got 3 different rates of change. These had a rate of change of 1. These two had a rate of change of 3. These had a rate of change of 5. This is considered a variable rate of change, which means this function right here is nonlinear. Now let's take a look at this other one. I'm going to do the same thing. I'm going to look and see how the x's are changing, and I'm going to look and see how the y's are changing. So on the side of the x's, this one from 0 to 2 increases by 2. This increases by 2. And on the y's, we increase by 3 from 4 to 7, and from 7 to 10, we also increase by 3. And then if I were to divide that, 3 divided by 2 would be 1.5, or 3 over 2. 3 divided by 2 again would be 1.5, or 3 over 2. I have the same values for both rates of change, which means this function in this table is linear. Now, equations are also really easy to tell, just like graphs are, because there are a few things you look for in an equation that tells you if it's linear or not. Now, every equation that's linear can be written as y equals mx plus b. That's the rule. Doesn't always mean it will be written that way, but it can be. That means that you could not have exponents. I had to think about what I had here. You could not have root symbols. You could not have absolute value bars. Something else I did not include, and I meant to include in this slide and forgot. You also cannot have x on the bottom of a fraction. So if you have something like 1 over x, that makes it nonlinear. If you have something like 1 over 2x and the x is out beside it, this is okay. So if you ever end up with x on the bottom of a fraction, like there's a fraction bar and the x is underneath it, then that's a nonlinear situation. So look at these examples over here. This one, where I have 2x plus 3y equals 5. It's not currently in this y equals mx plus b form, but because it does not have exponents, it does not have root symbols, it does not have absolute value bars, it does not have a fraction with an x in the bottom, it is still linear. We could rearrange that, and we'll learn how to do that later, to get a y equals mx plus b equation. So this function is linear. The one to the right of it, the y equals the absolute value of x plus 2, has absolute value bars in it. So even though it looks like a y equals mx plus b function, it's not linear because it has these absolute value bars. So the absolute value makes it nonlinear. The one on the bottom left here where it's x squared plus y squared equals 15, it's also nonlinear. It has exponents. This one, y equals 1/2 x plus 4. This x is meant to be out beside the 1/2. I know it looks a little bit weird because of the way it typed. But if you had y equals 1/2 x plus 4 and it looks like this, and the x is not under the bottom with the 2, which is how that's supposed to look. It just doesn't really look that way. That's linear. Your m can be a fraction. You just can't have the x on the bottom of it. Another thing you can do with equations, if you can't remember these rules, you forget them or whatever, you can always go into Desmos and graph your equation and look at the shape of it. If it's a straight line, it's linear. If it's curved, it's not. All right. Let's look at some examples of this. So we're just identifying linear or nonlinear based on the rules we just did. So this equation over here, this graph over here, we look at a graph and tell if it's linear or not by whether or not it's straight. This is a perfect straight line. This is linear. Now remember the table, you got to do a little bit of work to figure it out. And we do that by looking at our change from point to point in our table on both sides. So on our x's, we increase by 1 to go from 6 to 7. We increase by 1 again to go from 7 to 8. On the y side, to go from 19 to 10, we decreased by 9. To go from 10 to 3, we decreased by 7. So if I were to divide that out, negative 9 over 1, be negative 9, negative 7 over 1, be negative 7. They are not the same. That makes this nonlinear. All right, look at this equation. So in an equation, the things we look for to make things nonlinear is exponents, roots, absolute value, or an x on the bottom of a fraction. This has an exponent, so it is nonlinear. You also could have graphed that in Desmos. It would graph as an upside down U, which also would tell you it's nonlinear. All right, try these next 3 in your slides, and then come back and see if you were correct in what you decided. Just pause it, try them, and see what happens. All right, hopefully you paused it and are now back. And so this first one, you should have gotten nonlinear. And we know that because we have an exponent of x. The last one, you also got nonlinear. And we know that because it's not a straight line. The middle one, you had to do a little work to figure out. So to go from 1 to 2, we increase 1. Increase 1. Decrease by 8. Decrease by 8. So if I divided that, negative 8 divided by 1, negative 8 divided by 1 again is obviously negative 8. This one was linear. Now, sometimes you may be like, why is she dividing that when I can just see that they're the same? You can look at that as long as it's counting by the same thing on the x's. You have to be careful, though, if your x's are not changing by the same thing and you look at your y's to tell, you won't be able to tell from that. You have to divide. But in these particular situations, you didn't have to right there. So that's linear and nonlinear. Now we need to look at how we will calculate rate of change and slope. So rate of change is also called slope, and we'll refer to it as slope from here on out pretty much. But the slope of an equation represents how much it increases or decreases over time. It's usually indicated by words like each or per. So in a slope-intercept form of the equation, that y equals mx plus b form, the x and the y stay in there as variables, but you have a number in place of m and a number in place of b. The m that's with your variable is always your slope. If your equation is not written in slope-intercept form, but you need to know the slope of it, you can rearrange it into slope-intercept form just by solving the equation for y. So that's one way we can figure that out if you have an equation. If you don't have an equation and you're having to figure out the slope from a graph or on a table or from 2 points, there are really 3 different ways we do that. All of them involve division, but there's 3 ways that we do that division. So on a graph, you choose 2 points. I call them stop sign points. We'll do that in a minute. And you rise and run between those 2 points. So you do the rise or fall, if you have to fall. And you divide that by how far you have to run, left or right. So rise means you're going to go up or down. Run means you're going to go left or right. And you're going to divide the amount that you had to rise by the amount you had to run. That's going to give you your slope. On a table, you kind of do the same thing, but you divide the change in your y's, basically what we did on rate of change, by the change of your x's. Now, the good thing about a table is if you've decided it's linear, or you know it's linear, you only have to pick 1 point. You don't have to divide every point. You can just pick 1 point and divide the change on the y's by the change on the x's and get your slope, because every point you pick is going to give you the same value. And then if you have 2 points, you have to use the slope formula. So 2 points means you've got 2 different coordinates. And so we know a coordinate or an ordered pair is an x and a y. So when they write this formula, they refer to the x's and the y's as x1 and y1 when they come from the first one, and x2 and y2 when they come from the second one. So when you see these little bitty 1s and little bitty 2s, they're just telling you which x and which y to use. It is not an exponent, so don't mix that up. So the slope formula goes like this: y2 minus y1 divided by x2 minus x1. So we're going to practice some with all of this throughout this lesson. Now, slopes can be positive or negative depending on how the line goes. This goes back to our discussion in functions of whether functions were increasing or decreasing. A line that is increasing or rising from left to right is going to have a positive slope. A line that is falling from left to right is going to have a negative slope. And then a line that's not rising or falling, so that's going to be a line that's straight horizontal, has 0 slope. And then a line that rises forever would be a vertical line. It never stops going up. So that slope is considered undefined. So I have Mr. Slope Guy over here, and he can be kind of helpful in reminding you of what the different types of lines look like. A line that's going to have a positive slope will go up like this, like his left eyebrow. A line with a negative slope is going to go down like this, like his right eyebrow. A line with 0 slope will be like his mouth, and his dimples are the zeros. And the vertical line that makes his nose is undefined. So if you can remember kind of what he looks like, that can help you. The biggest challenge here is for people to remember if this is 0 or if this is 0, and if this is undefined or if this is undefined. So if you can remember his nose is undefined and his mouth is 0, that'll kind of help you keep that straight. That's Mr. Slope Guy. All right, and then we also want to look at y-intercept or initial value. And we're not going to focus a whole lot on this right now. We're going to do a little bit with it. But our main concern for this lesson is really about slope more than it is about y-intercept. But a y-intercept of a function is the point where the line crosses the y-axis. We learned that when we did other functions. That's the starting value in a linear function. So if you have a linear function about Johnny opened a bank account with $250 and he adds $50 every week to that account, that $250 that he started with is his initial value. It would be the y-intercept of your function. So in a slope-intercept form of the equation, y equals mx plus b, the m represented the slope, the b is what represents our y-intercept. So it's the number in the equation without the variable. So if you're looking for the y-intercept, you look for the point where the x is equal to 0. Sometimes that point will be given to you. You can look at it on a graph, just find the point where it crosses the y-axis. If you're not told the point where x equals 0 and you're not sure how to find it, we have a way that we can solve for b by subbing the slope for m and a point for x and y. And I'll show you how that works in just a minute. All right, let's get into some examples of this. So here we have a graph. We're going to look at finding slope and y-intercept from the graph. So to find slope on a graph, remember we said we had to pick 2 stop sign points, or 2 points, and we have to rise and run between them. Now, I always call them stop sign points. Let's see if I can zoom in on this real quick. And the reason we want to pick stop sign points is we've got to pick points that we definitely know the value of. So when I look at this line right here, there are several points that I would consider stop sign points. So as I start at the beginning of the line, this point right here at 20, I definitely know the value of that point. That point is located at 0, 20. It's perfectly on the line there. I'm going to look for other points that are perfectly on the line. I call them stop sign points because I'm looking for points that exist where 2 grid lines intersect, right in the middle of where 2 grid lines would intersect. But they have to be points actually along the line. So if I start here and I work my way up the line, the next stop sign point I come to is this one right here. And I can keep working my way up the line again until I reach this point right here. So this particular graph has 3 different stop sign points. I only need 2 of them to find slope. So the easiest thing to do is to choose 2 points that are as close together as possible. And ones that have numbers that are pretty easy to work with. So it really would not make much difference which 2 you use here, but I would use either this one and this one together, or this one and this one together. I would not start here and go all the way up to here. That's just going to make a complicated fraction for you to simplify. So we'll go with this one and this one just because that's kind of my normal common deal. So I'm going to start on the one that's the furthest left, and I'm going to either rise or fall to reach my next point. So from here, I've got to rise till I'm even with it, and then I can run to the right until I hit it. And once I do that, I'm going to count how much I had to rise and how much I had to run. Now, don't just count squares because sometimes it's going to be counting by something other than 1. So I've got to think, if I started at 20 and I went to 30, how much did I rise? I rose 10. If I started at 0 and I ran to 40, how much did I run? 40. So when I go to calculate the slope of this, I'm going to divide the amount that I rose, 10, by the amount that I ran, 40. And 10 divided by 40 becomes 1/4. Or you can express it as a decimal if it's nice and pretty, doesn't repeat or extend forever. So you can get 1/4 or 0.25. Now the b in the equation is the y-intercept. And I find that just by looking to see where the graph touches the y-axis. Now remember, your y-axis is this one, the vertical axis. So I need to look at the point where it touches the vertical axis. It touches it right here. The value of that point, the y value of that point is 20. So my b is 20. All right, let's go to this next one and look at it. So I'm going to do the same thing. I'm going to search for my m and my b by picking stop sign points for m and then rising and running to find its value. So if I start up here at the top left part of my graph and I work my way down, I'm going to just look for some stop sign points. So I see one right here. If I keep going, I see another one here. Keep going. Here's another one down here. Keep going again. Here's another one right here. And that's pretty much it. So I've got really 4 different points I could use. Again, it does not matter which 2 you use. You just want to use 2 that are close together. So again, I would use like this one and this one together, or this one and this one together, or this one and this one together. I don't really recommend you go from all the way up here to all the way down here and do that, because it's going to leave you some really big numbers and stuff that you might miscount. So I'm just going to use these top 2, because why not? So to get from the leftmost one, the top one there, to the next one, I have to fall this time. And then I'm going to run to the right again. We always try to run right because that helps me keep my positive or negative straight. If I fall, it becomes negative. If I rise, it's positive, and I'll always run to the right. So the bottom number is always going to be positive no matter what. So when I count this, again, I'm looking at what my graph is counting by. It labels every 20, but every line's actually 10, because it would go 10, 20, 30, 40, 50, 60, so on. So every box that I count, or every line that I count, is going to be worth 10. So when I go down this here, I go 10, 20, 30, 40. So I fell 40, negative 40. And I ran 10, 20, 10, 20, 30. So to calculate my slope, I would divide the amount that I ran, or my rise, negative 40, over the amount that I ran, 30, and I get negative 4 over 3. Now, if you were to do that in a calculator, you would get negative 1.3 repeating. You cannot put negative 1.3 repeating as your slope. You have to leave it as a fraction, negative 4 over 3. And then the B, remember, is that point where it crosses the y-axis. If I go back and look at that, I cross the y-axis right here, and the value of that point is negative 70. So my B is negative 70. All right. Go to the next one. Take a minute, pause this video if you feel like you can try this already, and see if you can find your slope and your y-intercept on these 2. Then come back and see if you were right. If you don't feel like you're ready for that and you need me to work through another 1 or 2 with you, then you can continue to watch. But it's good practice to try to do some on your own if you feel ready. So try both of them if you can, and then come back and see if you were correct. All right, hopefully you tried that with this. And hopefully in doing that, you got that this first one had a slope of 2 and a y-intercept at 20. And I'll show you where I got those values from, just in case you needed me to walk you through that. The y-intercept of 20 came from right here where that line touches the y-axis at 20. My slope came from using 2 stop sign points, and there were several you could have picked from here. Really, you could even use that way up there. I just used the first 2. And I figured that in doing that, I rose from 20 to 40, which means I had a rise of 20. And I ran from 0 to 10, which means I had a run of 10. And I divided 20 by 10 to get 2. All right. And then on the other one, when you did the other one, hopefully you got... I don't remember the answer to this one, so we're going to have to work it real quick because I don't remember what it was. Anyway, I know the B is negative 9 because I can see that. But let's see what the M is. For the M, you should have gotten negative 5 over 4. And again, we get that because from here to there, I have to fall 5 and run 4. And I divide that negative 5 over 4 or negative 1.25 if you put it that way. All right. Let's move on and look at how we do this with equations. All right, so in an equation, the slope and the y-intercept come from knowing what's in the right position when the equation is in slope-intercept form. You cannot tell the slope and the y-intercept from... You can't tell the slope and the y-intercept from an equation unless you put it in this form. So if it's not in this form already, we're going to have to rearrange it to get it there. Once we have it there, we know the m is the slope and the b is the y-intercept. So look at this first equation. The first equation is already in slope-intercept form, and I know that because my y is by itself, and I have an mx term and I have a b term over here. So because I know that, I can identify my slope and my y-intercept automatically. The m is the one with the x, the 3. The b is the one by itself, negative 4. There's no work to do on that. We can just see it and know it. Now, the next one, though, the x and the y are both on the same side, and y is not by itself at all. So this one's going to require me to rearrange the equation first. Here's how that works. We do a little bit of split the world action here. If I'm trying to get y alone, that means I have to find a way to get rid of this 2x and this 3. So we always move the thing not attached to the variable first. So I'm going to move the 2x term to the other side first, and then I'll deal with splitting the 3 from the y. So to move 2x, since it's being added or it's positive, I'm just going to subtract it. 2x minus 2x will become 0 and cancel out. But remember, if I subtract over there, I have to also subtract over here. Now, over here, when I do negative 12 minus 2x, that can't actually go together because neither one of those is like terms. 12 doesn't have an x, 2x does. So I can't actually put that together. I'm going to bring my 3y down. Now here, because mx plus b form puts the x in front, I'm going to reverse the order of this and put the negative 2x in the front and the negative 12 behind it. And then to split the 3 from the y, because I still need to do that. I can't have the 3 with the y and have it in slope-intercept form. So to get the 3 off of there, I'm just going to divide the 3, because the 3 is being multiplied by y. We divide it to cancel it. So the y will equal, now here's what's tricky, not really tricky, but here's what we want to make sure we know. If you divide by 3 over on this side, on the left, everything on the right side gets divided by 3. So it's not just the 2x and it's not just the 12. It's both of them get divided by the 3. It's kind of like doing distributive property, but with division. So negative 2 divided by 3 is negative 2/3 x. Negative 12 divided by 3 is negative 4. So now I have an equation in slope-intercept form, and I can tell you the slope and the y-intercept just by looking at it. The m, or the slope, is the negative 2/3, because that's the one with the x. The b, or the y-intercept, is the negative 4. And again, we can't see that unless we put it in, or we rearrange it into slope-intercept form first. Let's do one more like that together. So in this next one, I'm in the same situation where I have x and y both on the same side. I need to find a way to get y by itself. So to do that, I'm going to start by moving the 2x to the other side. Since it's being subtracted here, I'm going to add 2x to cancel it. So my 4y comes down. And this, again, because it's correct format to put the x first, I'm going to reverse this. Put the positive 2x in the front, the positive 16 in the back. And then the only thing I have left to do to get y alone is to get rid of that 4. And I can do that by dividing by 4. So y will equal 2 divided by 4 makes 1/2, or 0.5. You can write it either way. 16 divided by 4 is 4. So that means in that equation, the slope is 1/2. The y-intercept, or the b, is 4. All right. Take a minute, pause the video, see if you can get these into the correct format to see what the slope and the y-intercept is. Then come back and see if you were right. All right, so when you did this first one, hopefully you came up with a slope at -1/2 and a y-intercept at 5. And again, we know that because the one with the x is the slope, the one with the no x is the y-intercept. Now, the second one you had to rearrange a little bit. It was really simple to change it up, but you had to subtract the x off both sides so that you were left with just y. And so we get -x and +5 if you reverse that into the correct format. And so that means our slope is that number in front of the x, but there's not a number, there's just a negative sign. So remember, when you don't have a number there, it's understood to be a 1. So the slope is -1, the y-intercept was 5. And then in the last one, we had to kind of do the same thing we did on the slide before. We had to move the 2x first by adding it. And so that would give me 4y equals 2x minus 10. And so we divide everything by 4. And 2 divided by 4 is 1/2 x. -10 divided by 4 becomes -5 over 2. Or you might write this, because 2 divided by 4 is 0.5x. You could do that. And 5 divided by 2 is 2.5. You could have written it like that as well. So if you did that, m would either be 1/2 or 0.5. And b would be -5 over 2 or -2.5. Either one. All right, take a minute and pause the video again. And I want you to try the 3 on this slide back, and we'll go over them and see if you were correct. I'm pretty sure it just did some craziness when I switched slides. You're doing the 3 on this slide and the 3 on the next slide, so 6 problems total. All the problems off the top of the You Try Some pages there. All right, so when you worked these out, for this one, you should have gotten an m of -5 over 3 and a b at +1. This one, you got an m of 3 and a b at -4. This one, you had to do a little rearranging. Divide everything by 2. So you got y was -2x, +4. So your m should have been -2, and your b should have been 4. And then, and the 3 on that slide. And then come the last ones. You had to do a little rearranging on this one too. All you had to do with this one was divide everything by 3, because y was already on its own on that side. We just had to get rid of the 3 that was with it. So that gave you 1x and 4. So your m is 1. Your b was 4. To get y by itself on this one, you just had to add 3x to get rid of that -3x. Hope there's nothing with that. I really can't see that very well, y'all. So if there's a number over there and I don't know it, I apologize. I don't think there is. I can't move that or anything, so... Oh, look, I can do that. Just kidding. So all we do is add the 3x there. So y is equal to +3x, -6. So m is 3, b is -6. And then for this one... Now, I didn't tell you this before you started, so you might have been confused. Just because they don't label anything, you can just count it by ones. And so I would have gone from this point to this point, rows 1 ran 2. So you get a slope of 1 over 2, 1/2. And a b is located right here at -2. And we get that -2 because our origin is here. That's 0. And so you go down 2, brings you to -2 along the y. Okay, so this is notes from our first day on this lesson. So I'm going to stop this video here, and I will pick back up with the rest of this for a second lesson's notes in just a few minutes.